Welcome everyone, and thank you for joining us today. I'm excited to introduce our presentation titled Blueprint for a Clean Hydrogen Economy. Today, we'll explore how to overcome the iridium bottleneck in PEM water electrolysis through solution combustion synthesis. We'll also look at the intersection of materials science and commercial scalability, which is crucial for advancing sustainable hydrogen technologies. So, let's dive in and see how these innovative approaches can shape the future of clean energy. Let's take a closer look at the current state-of-the-art in this field. As you can see, it requires a very high loading of precious metals, around 3 milligrams per square centimeter. This high demand makes large-scale commercialization quite challenging and economically unviable. Essentially, the cost and resource requirements are significant hurdles we need to overcome. Now, focusing on the oxygen evolution reaction, or OER, which is a critical step in many energy conversion processes. OER is known to be highly energy demanding, meaning it requires a lot of input energy to proceed efficiently. This is why the choice of electrocatalyst is so important. The most active and corrosion-resistant electrocatalyst currently available is iridium oxide, or IRO2. It's considered the best option we have, but it's also rare and expensive, which again impacts scalability. Moving to the bigger picture, this process is part of a larger energy loop, where renewable energy and intermittent electricity sources, like solar or wind, generate excess electricity. This excess energy can be used for electrolysis to produce hydrogen from water, which then can be used in fuel cells to generate power or as a clean fuel source. However, despite these promising technologies, there's a microscopic roadblock we need to address: the high cost and scarcity of materials like iridium and the energy demands of OER. Overcoming these challenges is essential to making the distributed clean energy system truly practical and sustainable. Let's take a closer look at how our new method works. First, the output is a pure phase, ready for immediate use. It's a highly dispersible product straight from the crucible, meaning it's easy to incorporate into various applications without additional processing. As the process unfolds, evolving gases naturally produce highly active, microporous structures. These tiny pores increase surface area and reactivity, which is a big advantage for many uses. The high temperature gradient during synthesis helps to annihilate volatile impurities, resulting in a cleaner final product. One of the key benefits is that this is a facile, one-step autothermal reaction. It simplifies the process, saving time and energy compared to traditional methods. Now, moving to the advantages and post-processing steps, it's important to note that fine particles, if not controlled, tend to agglomerate uncontrollably. This can ruin ink dispersibility, which is a critical factor in many applications. Traditional methods often require heavy washing and thermal treatments to remove impurities, especially chloride residues left from synthesis below 500 degrees Celsius. These impurities can be problematic, requiring additional steps to clean up. In contrast, our SCS method, or solution combustion synthesis, offers a breakthrough. It replaces those tedious, multi-step traditional methods with a more efficient process, reducing complexity and improving purity. Overall, this new approach not only streamlines production, but also enhances the quality of the final material, aligning perfectly with our goal of innovative, sustainable solutions in material synthesis. Let's take a closer look at how this process works. This violent autothermal reaction is key because it ensures that the IRO2 crystals remain constrained to an extremely small nanoscale, specifically between 3.5 and 12 nanometers. This tiny size is crucial for catalytic activity. During the process, at around 400 degrees C, there's a rapid and voluminous evolution of gases. This intense gas release actually physically obstructs the grain growth, preventing the crystals from growing larger. This microscopic obstruction is what keeps the catalyst's structural integrity intact, maintaining its purity at the microscopic level. When we combine this with the fact that we're mixing in a stoichiometric way, it results in a very efficient, one-step, autothermal recipe for creating nanostructured catalysts. All of this aligns with our overall goal: to develop structured, phase-pure catalysts that are both effective and stable. This process highlights how controlling reaction conditions at the nanoscale can lead to significant advancements in catalyst design. Let's take a closer look at the data here. As we increase the Ur-Al-G and Ur-Mg compositions, we see a notable rise in the sharp Ur-O2 crystalline peaks, which appear at the exact 2 theta position in the map. This indicates that at these compositions, the formation of crystalline Ur-O2 is optimized. Moving on to the results, we observe the formation of embedded nanoneedles, which significantly boost the surface area, up to 131 square meters per gram, with a large portion coming from micropores, specifically 86 square meters per gram. This increase in surface area is crucial because it enhances catalytic activity and overall performance. Now, looking at the inputs for the Ur-Al-G series, we're combining Ur-Cl3, glycine, and aluminum, which leads to this distinctive sponge morphology. Interestingly, the Ur-Mg series, where we replace aluminum with ammonium nitrate, results in a porous sponge structure with a surface area of about 89 square meters per gram. This comparison highlights how tweaking the chemical inputs, like substituting aluminum with ammonium nitrate, can dramatically influence the structure and surface area. Ultimately, by optimizing these chemical inputs, we're aiming to identify a structural champion, a configuration that maximizes surface area and improves catalytic properties. This part of the study underscores the importance of fine-tuning the chemistry to achieve the best possible material characteristics. Let's take a closer look at the notebook LM concept here. We're working with a microporous alumina scaffold, which provides a stable structural support. Inside this scaffold, we lock in iridium nanoneedles, creating a highly active catalytic surface. These microporous structures are crucial because they maximize surface area and facilitate efficient reactions. Now, a key challenge in this field is that using an insulator as an insulator to an anode catalyst would typically hurt performance and cause rapid corrosion, especially in the highly acidic PEM environments we're targeting. But here, where the alumina comes into play, the so-called alumina anomaly. Instead of acting purely as an insulator, alumina can actually be used strategically to boost conductivity, which is quite counterintuitive but very innovative. Moving on to the catalyst blueprint, the goal is to combine these elements effectively. The hyperactive iridium nanoparticles, just 1 to 2 nanometers in size, are designed to maximize catalytic activity. By integrating them within this carefully engineered scaffold, we aim to create a robust, hyperforming catalyst system that overcomes traditional limitations. Overall, this approach connects the structural design with the functional performance, pushing forward our capabilities in PEM technology. It's about turning materials that are typically seen as insulators into enablers of better conductivity and durability. Let's take a closer look at slide 7. Here, we see how G-Notebook-LM's EDX validation confirms the material's detailed structure. The elemental mapping clearly shows that the supporting body contains both AI and Ur, indicating a mixed composition, while the needles are composed of pure Ur. This is crucial because it demonstrates an intimate, anchored dispersion at the submicron level, which is essential for stability and performance. Focusing on the needles, they are made of polycrystalline Ur-O2, oriented along the 110 directions. This orientation helps optimize their electrochemical properties and physical stability, especially since they are physically anchored into the support. Now, the matrix itself consists of amorphous gamma lumina supports with tiny, highly crystalline Ur-O2 nanoparticles, ranging from 1 to 2 nanometers, that are perfectly dispersed. This uniform dispersion is key to maximizing surface area and catalytic activity. Finally, the high-resolution mapping confirms this embedded anchor architecture, showing how the Ur-O2 nanoparticles are securely anchored within the alumina support. This architecture is fundamental for achieving the durability and efficiency we're aiming for in our application. Now let's take a closer look at how the particles behave during ultrasonication. As you can see, particles remain perfectly suspended even after just 5 minutes of ultrasonication. This is a crucial point because it indicates that the particles stay evenly dispersed without settling or agglomerating prematurely. Speaking of agglomerates, the heavier ones, ranging from 0.5 to 1 micrometer, tend to sink in isopropanol ink. This sinking behavior can be a challenge, but it also highlights the importance of achieving a stable dispersion. When we talk about superior ink dispersibility, we're essentially referring to how well the particles stay dispersed over time. This quality is key because it unlocks the potential for scalable manufacturing of membrane electrode assemblies, or MEAs. In the context of our overall theme, which is improving the efficiency and scalability of fuel cell production, these advancements in ink stability and dispersibility are vital. They help us move closer to more reliable, cost-effective, and large-scale manufacturing processes. Let's take a closer look at the performance data here. The LR-Al-G catalyst reaches a current density of 1.78 A per square centimeter at just 1.8 volts. What's really remarkable about this is how it jumps straight from being a laggard to matching the performance of elite commercial standards. This indicates a significant breakthrough in activity. Meanwhile, Ag matches the current state-of-the-art commercial performance levels, demonstrating its competitiveness in practical applications. If you look at the graph, you'll see how the current density scales with voltage, from 0.2 up to 1.6/cm2, illustrating the efficiency gains we're achieving. The slide also references the commercial MEA, or membrane electrode assembly, and highlights the SCS efficiency gain, which points to how our catalyst blueprint can improve overall system efficiency. The polarization racetrack concept here is about minimizing energy losses during operation, which ties into the catalyst design and how we optimize performance. Overall, these results underscore the importance of the catalyst blueprint we've developed, showing not only high activity, but also a clear pathway toward commercial viability. This is a key step forward in advancing fuel cell technology and meeting the demands of real-world applications. So, moving on to our final slide, the verdict here is a statistical tie. This indicates that, based on the data we've analyzed, neither approach clearly outperforms the other. It's essentially a close call. Now, when we look at the overall verdict, we can see it's considered highly stable. This is significant because stability is crucial for long-term applications and commercial viability. The slide also features what we call the commercial showdown matrix. This compares different catalyst systems, specifically aiming to achieve commercial parity while using about 45% less of the precious metal, so that's a substantial reduction in material costs. Let's take a quick look at the table data. On the left, we have the SCS Ag MEA, and on the right, the commercial standard with Ru-Ox. In terms of current density at 1.8 volts, the SCS Ag MEA shows 1.78/cm2, while the standard is at 1.8/cm2, so very close performance-wise. When we consider long-term stability, the SCS Ag MEA runs at 0.635/cm2 over 160 hours of continuous testing, which is quite promising. The baseline for comparison is maintained here, indicating consistent performance over time. As for catalyst loading, the total amount of catalyst used is 2 mg/cm2 for the SCS Ag MEA, compared to 3 mg/cm2 for the standard. This reduction aligns with the goal of using less precious metal without sacrificing performance. And lastly, the active iridium loading is 1.65 mg/cm2 for the SCS Ag MEA, which is significantly less than the 3 mg/cm2 in the standard, again emphasizing material efficiency. Overall, these results suggest that we're nearing a point where cost-effective, stable, and high-performing catalysts are within reach, and this comparison underscores the progress we've made toward that goal.